Hey, good afternoon, and welcome back to my channel here. Today I'm going to talk about a drug that's actually fairly important, and it's very common, and it's also kind of been in the news a bit lately. And so, if you probably haven't guessed, we're going to talk a little bit about Tylenol or acetaminophen, right? Now, I've actually got a 3D printed structure of Tylenol right here, right? And so let's just kind of look at this structure and look at what we have on here. We have the phenol over here. So we have a phenyl ring. This is the phenyl ring, and this is the phenol OH. So that's the alcohol attached to the phenyl ring. We have a nitrogen. So that's the blue right here. And so that's the amino group. And then over here is the acetyl group, and it's called an N-acetyl group because the nitrogen is immediately adjacent to the acetyl group, right? So it's a fairly simple structure. It's actually not very complicated to synthesize, and it's been pretty widely used. And so this drug has been widely used for acute migraines, and it's got antipyretic effects. Because it actually acts on the brain in the temperature regulating mechanisms. So it actually causes vasodilation, so it helps to relieve fever. And it's also not addictive, so it's non-opioid based, but it's not really a member of the non-steroidal anti-inflammatory drug class, which contains aspirin and ibuprofen. It has some similar effects to that class, but it's not exactly, it has a weaker prostaglandin inhibition, which makes it a little bit safer than many of the other non-steroidal anti-inflammatories, although it's still, not without a certain amount of caution as with any drug. So let's kind of look first of all at how we get the name Tylenol or acetaminophen, or if you're in Europe, you're probably familiar with the name paracetamol, right? So that's actually the more common name globally. I think in North America and Japan we use acetaminophen and Tylenol, but globally the drug is actually known as paracetamol instead. Now, all three of these names, interestingly enough, are derived right from the structure of the drug. And so if we just kind of look at the structure, I'm actually going to draw that on my little whiteboard here. I'm going to start drawing the phenyl ring, and then I'll draw the OH. And then so N-acetyl para-aminophenol. So if we remember ortho, meta, and para, right, from organic chemistry. Para, meta, and ortho, right? Now, these are referred to substituents on a benzene or an aromatic ring. So if you have two substituents that are opposite size, that's going to be called para. So those are, opposite on that benzene ring. Now, if you have two substituents that are kind of like this, at like a 120-degree angle from each other, with a hydrogen in between, that's called meta, right? And then the last one, of course, we can look at the substituents that are located adjacent to each other on that benzene ring, and that's called ortho, right? So the substituents in acetaminophen are para. So that means that if I have a phenol, or if I have a phenol, I need to connect my amine exactly opposite of that and make it para, right? And then connected to the amine, I need to connect my acetyl group. And so that acetyl group, anytime we have a carbonyl, so that carbonyl is the C with a double bond to an oxygen. That's and then that's called a carbonyl group, right? So just that part is the carbonyl. And then right over here, we have a methyl. And so if you have a methyl carbonyl, collectively I'm going to call this an acetyl group. And we see these throughout biochemistry and organic chemistry. As a matter of fact, acetyl-CoA, which is central to our metabolism, is so named because really the activated portion on the end of that is the acetyl group. So there's our acetyl group. The next part we're going to look at is right here, and that's just the amine. There's our amine functionality, and then I'm just going to circle this, and that's the phenyl ring. So that's just by itself. And then lastly, if I take, whoops, I didn't quite get the colors. There we go, in purple. That OH, now that OH is normally called a hydroxyl or an alcohol, but because it's connected to an aromatic ring, I call that a phenol, right? So that's how we get the name phenol out of that. And then, so if I look at the name for this drug, or the name for the compound really, I'm going to call it N-acetyl para-amino phenol, right? That's the long name for the compound. Now, when we're designing drugs and we're designing compounds, we like to come up with a name that's going to be a little more recognizable, a little bit easier for your average consumer to make it. And let's just put it this way. I don't think Tylenol would be sold and widely available in most people's medicine cabinets if it was called N-acetyl para-aminophenol. That kind of chemical names often are a bit scary. So drug companies come up with shorter names for it, right? Now, all of these shorter names are actually all derivatives of the full name of the drug. And so let's just kind of break that down. If we break down, let's start with acetaminophen. So that's acetaminophen. That would be acetaminophen, right? So that's the common name in the United States and North America. So that's directly derived from the full name. Tylenol is also derived. So we take the TYL from acetyl and the ENOL, and that's how we get Tylenol, right? So we get the name Tylenol directly from the name. And then for the more common name globally, I'm actually gonna, let's do para-acetamol, right? Paracetamol. Paracetamol is probably the more common pronunciation of it, but that's also derived from the name. A little bit different because they put the para before the acetyl, and here it's after. But you know, okay, you kind of get the idea. So, but it's kind of cool because you know, usually when chemists name something, we base it off of our observations. We base the name off of the structure that we're designing. And hence, it makes it a lot easier to kind of recognize and work with. And all of the names point back to the ultimate structure of the drug. So that's really good in there. Now let's kind of look at the history of paracetamol. And so this drug actually goes back to 1877. with it was first synthesized by Harmon Northrop Morse. And so he was a scientist at Johns Hopkins University in Baltimore, right? And so he first synthesized this compound. Didn't really figure out what he was going to do with it quite yet, but he had originally synthesized it by reducing paranitrophenol with tin and glacial acetic acid. So he kind of used that basic synthesis to make the drug. And then by 1887, another scientist, Joseph von Mering, he's a clinical pharmacologist, and he's the first one that first used this drug in humans. And so now it's actually, of course, this was kind of predating the FDA approval process. You know, this is the 19th century, a long time ago. We now kind of, you know, I guess this would be called the Wild West of drug discovery. We kind of started to look at compounds that might be beneficial pharmacologically, but there wasn't too much of an approval process. So we just, you know, they came up with stuff. So 1887, they're first using acetaminophen, probably not under that name, but they're first using this compound in humans. Now, that takes us to the 1950s, and this is when, you know, we have gone through a lot more, and we're starting to get into more modern drug discovery in that era. So in the 1950s, under the brand name Trigesic, this was where the compound was first sold and marketed for the treatment of fever and acute migraines and that sort of thing. And it worked fairly well. And then by 1955, it was approved for over-the-counter use. And so now you could get this drug without a prescription. So that was also a major stepping point in the drug's history. So now we can kind of start using it. Since then, it kind of has been used as a common headache pain relief process, as a common drug for that. And also it's very good for reducing fever. It's also been recommended by many physicians for the treatment of, you know, fever and pain relief during pregnancy, which that's a very important consideration because there's not a whole lot of drugs that you really want to take while you're pregnant, because not only could it affect you, but it could also affect your fetus as well, and so that could affect fetal development. So there's been a lot of concern, a lot of interest in finding drugs that pregnant women could take that would not affect the outcome of the fetus. And most doctors, even today, will agree that Tylenol is still generally considered safe for pregnancy. Although if you have concerns over specific conditions, everyone is different. You should, of course, talk to and discuss this with your physician if you have specific concerns, right? So I wouldn't just take one specific advice. Your physician can look at your medical history and your case profile to make the best decision for you, right? So that's important there. Now, why is this? Because, you know, obviously pain, you know, dealing with short-term pain, and we're talking about acute pain versus like chronic pain would be something long-term. You probably want something a little bit different, because I would not take Tylenol or actually any of the non-steroidal anti-inflammatory drugs for chronic pain, because long-term use is associated. First of all, the non-steroidal anti-inflammatories work by inhibiting an enzyme called cyclooxygenase. Cyclooxygenase. oxygenase, and we can just call that COX, and there's two forms. There's COX-1 versus COX-2, right? Most of your non-steroidal anti-inflammatory drugs will inhibit both of these forms of the drug. Cyclooxygenase 2 is what actually mainly causes the pain relief. The cyclooxygenase 1 is commonly found in the gastrointestinal tract, and therefore a lot of these drugs will have gastrointestinal side effects, which you probably don't want, because that could ultimately lead to ulcer in the long term, and it could cause a lot of, in the short term, it could cause gastrointestinal discomfort. So that's one of the disadvantages of taking non-steroidal anti-inflammatories long term. Now, Tylenol is not really the same as aspirin or ibuprofen. It's got a different profile. It does inhibit cyclooxygenase, but it doesn't inhibit that quite as strongly, right? So because of that, it has fewer of those gastrointestinal side effects, but there is a danger for liver toxicity. And so that is one of the major concerns with Tylenol there. So again, if you have concerns about taking the drug, every patient is different. Again, talk to your physician if you have specific concerns there. So that's always important. Now let's talk a little bit about how we synthesize acetaminophen. And obviously the first synthesis over 100 years ago was by reducing paranitrophenol. Well, we need to get that paranitrophenol. So what is paranitrophenol? Well, you're going to have an OH, and you're going to have a nitro group on it, right? Now, in order to get this, most classical syntheses will actually just treat phenol, which you can get fairly easily, with nitric acid, right? So that's HNO3. And then you get that paranitrophenol. Now, we need an amine, not a nitro group. So what we have to do is then reduce the nitro group with H2, and we need rainy nickel to do that reduction, right? So that will then convert that nitro group to an NH2, right? And so now we have an NH2 on there. I think that's so, and then what we have to do is we have to acetylate this, right? So what we have to do is we're going to take acetic anhydride. So acetic anhydride. You could think you could just use acetic acid, but I think they're going to find acetic anhydride a little bit easier to work with. It's actually going to end up giving you acetic acid. So acetic anhydride kind of looks like this. It's got an ether oxygen between two carbonyls like that. That's acetic anhydride. And what essentially happens here is this nitrogen essentially attacks the carbonyl, and then this comes off and then that comes off as acetic acid. And then what you're going to end up with is essentially your acetaminophen. So that's acetaminophen, and then you also get acetic acid, which I just drew acetate, but that that's the conjugate base. So this is kind of the classic route of synthesizing acetaminophen right there, and so that's essentially how we make it, right? So that's acetaminophen. Now, the drug's not without controversy. So let's talk a little bit about some of the issues. Now, first of all, historically, acetaminophen has had an interesting history. Of course, it's very widely used throughout the 60s and the 70s. When we get to 1982, it got kind of interesting. And I actually grew up in Chicago, and I lived in Chicago until 1985, and I was in the Chicago suburbs, Elmhurst to be specific, and in 1982. And at this time, this was when a rather deranged individual was decided to take Tylenol capsules. At the time, they sold Tylenol in a capsule that you could actually open, and then you can remove the medication from and all that. That they sold it in those. So he removed the capsules, and then he put cyanide in the Tylenol capsules. So he tampered with the package, and they put it back on the shelves. People bought it, and then they poisoned themselves with cyanide poisoning. Cyanide works by inhibiting complex 4 of the electron transport chain specifically, and it shuts off your electron transport chain. If you've seen the movie Oppenheimer, J. Robert Oppenheimer was a little ticked off with his professor because he wouldn't let him go to a Niels Bohr lecture that he really wanted to go to, and so he decided to get back at him by injecting potassium cyanide into an apple, hoping to kill him. Unfortunately, that didn't work out. He never killed his professor. There's also some debates over the truth to that story anyway, but it made for a good Hollywood theme, and so that's kind of where we got Oppenheimer involved in cyanide. So yeah, cyanide is definitely a very potential potent poison, and so this guy in Chicago was putting cyanide into Tylenol capsules, and it caused a major stir. I actually remember my parents going through the medicine cabinet looking for all the lot numbers on all the cyanide, the cyanide or the Tylenol packages, and trying to figure out. And eventually, they just said, "Screw it, we're just going to throw out all the Tylenol, and we're just going to wait until this resolves itself eventually." But at the time, McNeil Laboratories, I think they were owned by Johnson and Johnson. They lost a lot of customers that way as a big concern, and they had a lot of damage to do because of that, and a lot of damage to deal with. They actually dealt with that very well, and I would say Tylenol has recovered as a drug in terms of the confidence of the public because of all the public relations work. It's kind of a model for good public relations. The first thing they did in response to the incident, a couple things they did. They changed their capsules. Instead of having a capsule that could be opened, they changed that to a gel caplet. So it's now a gel-based molecule that you couldn't open, and the drug was all fixed inside there. So, and they made sure everyone knew what a Tylenol caplet would look like. They also reinforced the packaging so that it would be very obvious for someone to detect if that package had been opened or not previously, or tampered with. I guess tampering would be the correct term there. So this helped to restore confidence in the public for Tylenol again, and their market, the drug kind of rebounded, and people started buying it again, and so that was really big. Now, last week, we have another little problem with Tylenol, and this deals with our government that decides they released, they're going on some so-called studies that suggest that Tylenol is the main cause of autism. And so the president and the Health and Human Services Secretary are now recommending that mothers do not take Tylenol when present. And they're just saying don't do it because your babies are going to end up autistic, and this is a big problem, and so we need to solve that problem. So let's first of all think about what autism is. And so autism, it's not really a disease. It's actually called autism spectrum disorder now, ASD. The autism really goes back to 1911 when it was first the term was first coined, and then they started looking at it in children. And now we kind of know it's more of an autism spectrum disorder instead of a specific disease or condition. So it's really a broad spectrum, and it's a developmental condition that affects how a person communicates and how they interact with others and how they overall interact and perceive the world around them. So it's dealing with a lot of sensory issues as well. And many people with autism actually have a lot of unique strengths. They have strong memory. They have very good attention to detail. They're very creative in problem solving. Some of them are just very good at specific tasks. But they also have a lot of difficulty in social situations and changes in daily routine and just routine in general. They are also very highly susceptible to sound, light, and even certain sounds or lights or even specific textures, and that can be very challenging for them. And it affects everyone very differently, just like drugs affect individuals very differently, right? Some people may be allergic to some drugs. Some people a drug may be effective on. Other people a drug may not be effective on. There's also a spectrum there. Everyone is different. And even on the autism spectrum, autism affects different people differently. Some people are very severely affected by autism and they need specific care for probably the rest of their lives. Other people have a mild form of autism and they can function, they can hold down a job, they can actually participate socially, but they do have certain challenges that they need to deal with. So they need some support, maybe not as much as others. I don't really see autism as a disease that really needs to be cured. I don't think we're ever going to find a cure. And I also don't think there's going to be a specific cause of autism. What causes it? A lot of scientists are thinking that the biggest factor is genetic disposition. So your own genes are probably one of the biggest factors because these are characteristics that seem to be inherited as opposed to things that, there's specific things in the environment that cause it. But there could also be things in the environment as well. It's really just a different way of thinking and a different way of experiencing life. So, and again, some people are very severely autistic, others not so severe. And so we need to understand and we need to give these people more acceptance in helping people with autism to share their unique talents and to allow them to thrive in school, in work, and even in relationships as well. So that's kind of where we are with autism. So I don't think Tylenol is causing autism. There can be some very specific associations between Tylenol use and autism. There have been several studies, but many of these studies are really inconclusive on whether Tylenol is actually causing that autism. It's kind of like another thing. And if we kind of look at, I'm going to draw a little graph on here. And let's just kind of make the x-axis, I'm going to make time. And I'm just going to go time from January to December. We're going to make that 1 year, right? And so what we're going to look at is the correlation between two different things. I want to look at ice cream consumption. And so let's look at ice cream consumption, because most people like to eat ice cream. We mainly eat ice cream in the summertime, so we're going to maybe in the wintertime, as we go into spring and summer, ice cream consumption rises, and then it's going to peter off again as we go towards the winter months and into December, and then it'll rise again the following year. Now, the other thing that we can look at is snake bite or snake attacks, right? Now, snakes are cold-blooded, and so their temperature is based on the temperature of the environment. And so during the winter months, snake bite activity is at a minimum, and then it rises somewhat over the summer, and then it falls again as we go back into the winter, right? So there's definitely a correlation between these two things. Does that mean that if you eat ice cream, that's going to somehow be attractive to a snake and it's going to drive all the snakes towards you to bite you? No, not at all. The snakes they don't care about the ice cream. The snakes will attack you if you threaten it. And if you just leave the snake alone, it generally will not attack you, right? So there's no correlation here. In other words, correlation does not mean causation, right? And that's the same thing with acetaminophen and Tylenol, or acetaminophen used during pregnancy and Tylenol. There's a correlation, but that doesn't mean there's a causation here. So it's two completely unrelated things. Now, there is one thing that is correlated between acetaminophen and snakes, right? So that's another interesting correlation. And this actually goes back to Guam, where during World War II, when the United States was fighting in the Pacific, we introduced the brown tree snake into Guam, and that was an invasive species. It was not on the island before. And so then what they kind of noticed with this brown tree snake was eating, they were, eating some of the other rodents on the island, like rats and mice, and that was causing a decline in those populations, those native populations. And in order to deal with this, they actually discovered that if they took Tylenol capsules, just 80 milligrams of Tylenol, and they put that into a rat or a mouse, and then the snake would eat that, the snake would die. They eventually determined that the Tylenol, the 80 milligrams of Tylenol, was killing the snakes, right? And so Tylenol will actually kill snakes. So if you're a snake, don't eat Tylenol at all because it will kill you, right? So now, why is this? What causes this? So here's the science behind that. And this is also true of cats as well. So if you're a cat owner and you think your cat has a fever or a headache, don't give your cat Tylenol either. Because snakes and cats and some other animals, they lack an enzyme involved in the metabolism of Tylenol. And that enzyme is UDP, glucuronosyl transferase. And we're just going to call this UGT for short, right? So this is an enzyme in the pathway that breaks down Tylenol in your metabolism. And humans have this enzyme. Dogs, horses have this enzyme. That's why you can give Tylenol in veterinary conditions to dogs and horses. But cats, snakes, I think some turtles and some reptiles, maybe frogs, I think, they don't have this enzyme, so that makes Tylenol, they can't metabolize Tylenol, so then it builds up and that becomes toxic to that organism. And so then the organism's going to die because of the Tylenol. So don't give Tylenol to these organisms, right? because they lack this enzyme, and then that's going to be toxic to them. So that is an interesting correlation there. So, all right, so that's a lot of information about Tylenol. We kind of learned about where it came from and how to synthesize it, and a little bit about the history and its connection to autism. So I hope you found this very interesting, and here's my 3D print of my Tylenol molecule once again. And if you like these videos, go ahead and hit the like and the comment button. Go ahead and subscribe to the channel so you kind of are notified of more stuff. And again, I'll see you in another video. Thank you for watching.